bombarding you with questions.
We're
So,
on. Everybody, welcome to the Tuesday evening space show program. I'm your host, David Livingston. Thank you very much for tuning in. Bill Gowan, this gentleman right here, hopefully my cursor is pointing to him on your screen, is going to be a co-host with us tonight, and I will turn it over to him in just a minute. I do want to make a couple of quick announcements. You should listen to the Hotel Mars program when Bachelor archives it tomorrow because he has UK special guest on. John Hunt, you will love this because SETI has a new plan about disclosure. And Michael is in the UK in Manchester at the University of Manchester, and he's heading that program. Now, I'm not clear if he's heading it for SETI Europe, if there is a SETI Europe, or if it's for SETI everywhere. But I've been joking around with him a little bit in the emails about the Spielberg movie. But that's Hotel Mars. There is no show on Friday for me to do non-space show business. And the guest planned for Sunday, Lisa Levante, who many of you may know, switched the dates. And Lisa is going to be on Sunday, July 19th. So this Sunday is an open lines discussion. And hopefully all of you, or at least some of you, will be able to join us. And we look forward to that. Bill, as many of you know, is a really good, great, wonderful personal friend of mine. He's very active in advocating and lobbying for space, goes to Congress every once in a while, and gets a little dirty with them to get his points across. And he goes to ISDC. He's a strong participant with National Space Society. He's in North Carolina. We forgive him for that since they have too many good sports teams. And he met Jim at ISDC, and Dr. Green has been a guest on the space show a couple of years back. I think he's been on twice, maybe. And we welcome him back. And Bill, go ahead and do your thing. And we appreciate your being here.
sure, thanks, David. I'll do the intro for Jim. So, Dr. James L. Green is an internationally recognized space physicist, planetary scientist, and former NASA chief scientist whose career has helped shape modern space exploration. During more than 4 decades with NASA, he has led scientific investigations, directed some of the agency's most ambitious robotic exploration programs, and helped define the strategy that ushered in a new golden age of planetary discovery. From exploring the physics of the space environment to overseeing missions across the solar system, Dr. Green has played a central role in expanding humanity's understanding of the universe. After earning his PhD in physics from the University of Iowa in 1979, Dr. Green joined NASA's Marshall Space Flight Center in 1980. Today, Dr. Green continues to inspire the next generation of explorers through research, education, and public engagement. He founded Space Science Endeavors LLC, where he continues to publish on topics ranging from planetary exploration and astrobiology to space weather and human missions to Mars. He also founded MetaVisionaries US,
US.
which uses immersive virtual reality and metaverse technologies to teach students around the world about astronomy, planetary science, and space exploration. Through these efforts, along with his public lectures, advisory roles, and ongoing scientific research, Dr. Green remains one of the world's leading advocates for humanity's continued exploration of the solar system. So, Jim, welcome to the Space Show.
Well, thank you very much, Bill. It's wonderful to be here again. I like talking about space. I teach space in the metaverse, as you said. I always got into that, and I'll just mention how that actually started. My interest in outreach really began when I was the division director of Planetary Science Division at NASA headquarters. We were in a budget crunch. I had interacted with the administration, and they were going to cut our budget over a 5-year period to about half of what it was. and it was running at about $1.3 billion. And I can't run a division that launches fabulous planetary programs and Mars rovers and flies by Pluto and all that stuff with a dwindling budget. So
what year would this be roughly?
2012. Yeah.
Oh, okay. Yeah.
2012. So I decided, well, how am I going to stop this? Well, Congress can stop it. The administration can give them the budget they want, and Congress can always up it. So how do we get to Congress? Okay, so as David mentioned, you go to Congress every once in a while, and I'm very familiar. I'd already done about 5 hearings, and so they work me over every once in a while. But if I got our scientists to go and lobby, that doesn't work, because they go and they only talk about their one thing. All right, and they look very parochial. So I went to a couple of the groups that like Lockheed Martin and others that build our spacecraft, and they said, no, we're not going to do that, because if we don't build a planetary spacecraft, we'll just go build an Earth science spacecraft. Doesn't matter to us. Okay, and I'm going, okay, that's the wrong group. Then it really, got to the point where I recognized I needed to talk to the people. I needed to do something where the general public understood a little bit about what we were doing in planetary science, and so I was able to capture into my group Kristen Erickson, who was a longtime NASA employee and really had done all kinds of outreach activities and well known in NASA. And I said, how do we connect with the public? And she goes, well, you have to think creatively. We're about ready to land Curiosity on the surface of Mars. Let's just film in the control room and broadcast it everywhere. Well, we never done that for a planetary mission or any of the science missions. Planetary runs on big events, mission insertion or flyby or landing or some really big thing happens, and it's always tense. And so I said, hey, that's a great idea. Let's do that. And I had Ed Weiler, my supervisor, come into my office one day as we were moving out with the concept of broadcasting this to all the other agencies. Every one of the centers were doing something. They were putting on big screens at Ames where 5,000 people would come into this big mall area and sit down and watch what's going on in the control room at JPL as we land this thing. He comes into my office, says, "What the heck do you think you're doing?" And I said, "Well, I've got to, bring the public along. I want them to see what we see. I want them to see the excitement and everything else that we go through, and they pay for what we do. So let's show them what it's like." And he goes, "Well, that you're way overdoing it. Now Ed was around when Hubble's mirror didn't work, okay? And so he got beat up mercilessly. And he says, what's going to happen if Curiosity crashes? All right? What about that? You do all this stuff, it's going to be on the front page, everyone will see it, and NASA will be embarrassed. And I said, well, if Curiosity crashes, I know exactly what will happen. That's my mission. That's a division mission. I'm the one that put the money on the table, went and got it, gave it to JPL to manage, but I'm ultimately responsible for it. And I said, well, if it crashes, somebody's going to get fired. I know who that is. It's me. You fire me. He goes, you're right. I'll fire you if it crashes. So he says, you're way too optimistic. I mean, you got, and we were talking about, this is what we're going to do. This is how we're going to do it. And he walks out of the office wanting me to cut back on the outreach activity. I'm sitting there thinking, well, really, he's right in the sense that I'm a very optimistic person. He's a very pessimistic person. Okay. So that was a clash of personalities. But there's one thing I took away from that, and that is I didn't really talk about what would happen if it did crash and what was the probability that it would crash and why are we worried about it if it crashes. And so we got JPL to do a little movie, and that movie is called The 7 Minutes of Terror. Okay. And that's all
Remember
about
that well.
yeah, I mean, so we broadcasted the heck out of that. Now that sets that actually heightens the climax, but it also sets a lot of the expectation. Now, one of the reasons why I was very comfortable in doing this, it was really quite simple, and that is Curiosity was supposed to launch in 2009, so it missed that window. All right, it missed the window. And it wasn't ready. We didn't, it was doing too many what I call miracles. And I learned from Curiosity, one miracle a mission, but Curiosity was doing like 10. It was huge. We never landed anything like that. It had 78 actuators. It was a 1-ton rover. It's 5 times more, much more than that, than the mass of the previous rover, which was Spirit and Opportunity. And we couldn't use airbags to land it. So it was the entry, descent, and landing. All that was new. Thicker heat shield, bigger capsule, bigger parachute. I mean, the parachute would fit over a 2-story house, maybe 2 2-story houses, and then the sky crane. What was that? Where did that come from? Crazy stuff. One thing after the So I went to Congress and I had to beg for $495 million more so that we could keep everybody working and we can go to the next 23 months later, the next planetary window. And so when that happened, then I would go out to JPL. While we were, they gave it to us. So I got the money and off we go. And I'd go and I'd say to the engineers at lunchtime, how are we doing? Well, we're performing this test and we're fixing that and this is happening. And, and it had all these ups and downs, but they were working out all the problems. And finally, it got to the point where I was asking the engineers, okay, what other money can I throw at you? I mean, this is a crazy thing to tell a contractor. Of course, they're going to tell you something, right? But they got to the point of saying, we're out of ideas on how to test this. Okay. We have tested it every way we can think about. And that's when I realized if this crashes, it must be an act of God, because from a human standpoint, these fantastic engineers have at JPL really did it. So I was very comfortable. I was very comfortable in how we tested it. And of course, we stuck the landing. Everybody saw it, and that's what really started me on this role of science isn't done until it's shared. All right. But that means something different now to me. When we do science, we go to scientific meetings and we present what we're doing, and it's at various stages. We interact with our colleagues, and then we write up a paper and we go through the peer review process. It's published, and then we move on to the next thing because we shared it. No, that's wrong. You have to share it with the public. So it's not done until some of these results are shared with the public. So tonight what I want to do is do a little of that. Okay, I've written several papers since I've left NASA. I have gotten really excited about the next frontier of what we need to know. When I was head of planetary, there were the discoveries of near Earth objects that needed to be made so we could determine if we were have a threat. All right, what's the threat level? And when I became head of planetary in 2006, we only had like $4 million. I'm supposed to find all the NEOs that's going to destroy this earth on $4 million a year, you know? And so we worked up the budget. And then in 2016, we created the Planetary Defense Office. Okay, we'd worked with the administration on a call down on what would happen if we found a NEO that's going to hit the Earth that is of consequence. You know, we had done tabletop exercises with Homeland Security, and turns out they really needed it because they had no idea what this was all about. And that was coming along. So these kind of things were real important, you know. So that's a recognition that we, living on this earth, must know what's happening all around us. Now, that means not only in our solar system, you know, where there's space weather and there's these huge coronal mass ejections that, you know, can cause enormous problems. And I did a lot of work on the Carrington event before I became head of Planetary. Carrington event is these huge storms that happened in our history that knocked out all the telegraphs and gave us a heads up that we're going to have some big problems. Okay. And then we worked on NEOs. Well, you know, the dinosaurs didn't have a program, space program. So, you know, they went by the wayside. And now we know a lot about NEOs, and that's coming along really well. In fact, we even got to the point of how to defend. By the last mission I was able to get money for that we executed was DART, which went out, hit an asteroid, moved it really successfully. You know,
More than expected, right?
Yeah. In fact, we just didn't realize how important that kinetic impactor is going to be, not only to that size, but now we think we can hit and move even bigger things because of that. And that's really good because we need to come up with other ways.
Jim,
So,
can I ask you a quick question?
yeah, sure.
Have you ever given thought to what percentage of the public needs to care about this and needs to be able to understand what you're doing? And can you further break it down, since you're global and you're teaching global students?
Right.
What's that percentage of the public for the United States? What is it for Europe? What is it for who knows where? Is it a percentage that's known for various parts of the world? But I'm more interested in this country. It doesn't seem to me like you're reaching the people we see on TV news every night.
Yeah, you know, I'm on the news a lot, actually. I was on for instance, the Artemis launch. I had 4 or 5 interviews, all over the place, and I used to be on CNN fairly regularly. But you're right. It should be a constant approach that people that are involved in these things do the outreach, and that's part of, you know, all our scientists need to recognize that science isn't done until it's shared, and that includes the public, as I mentioned before, and they have a role to play, and they must do that. Here's what's happening internationally. When I started in NASA, there was like 4 major space agencies. Okay, this is in the 70s. We got NASA, European Space Agency, the Japanese Space Agency, and the Russian Space Agency. That's it. Okay. And then CNES was coming along, and then several others, you know, and it kind of dribbled out. Right now, there's like 75 countries with space agencies. Okay. And when I was in Saudi Arabia as chief scientist, and we were talking about the Artemis Accords and getting them to sign up for the Artemis Accords, they had the Saudi Space Commission was trying to decide on what their space agency was going to do. And it turns out they had a really aggressive program. We're going to build missions, and we're going to go here, and we're going to go there. You know, we're going to do these things. And when I talked to them about, well, where are you going to get the people to do it? They said, well, we want to hire Saudis, you know. Well, yeah, all your countries with space agencies want to hire in their country. The problem is The universities don't even have aerospace classes or degrees, or there's nothing in planetary science. There's nothing in astrobiology. There's nothing in systems engineering, things that enable one to be able to hire. So they got to feed the pipeline. They got it, and that's how I got into the metavisionary business, because in virtual reality, you can sign up any kids anywhere in the world, and you put in a number and they walk into a spacecraft orbiting the Earth and talk to the former NASA chief scientist. And so up to now, I've taught about 5,000 students in the metaverse. But the bottom line is we've got a long way to go. We have a long way to go. In the United States, too, in particular, I think the exciting thing about the Artemis program was more and more people in the population really got it, really said, oh, wow, this space program is pretty exciting. And it's been taken for granted for a long time. So I'm really hoping more of the Artemis program will be unveiled over the next several years as they do Artemis 3, Artemis 4, land on the moon, and then begin preparations for humans going to Mars. So, and I'm involved in some of that research. It's one of those things I just can't let go. I'm constantly.
I got a question around that.
Yeah.
One of the things that excites people is the high risk involved in. And once makes them want to tune in and see if it actually is going to work. And if the missions are always low risk, or always been very, very well baked and tested beforehand, so nothing ever goes wrong, people won't be excited. So what do you feel about NASA taking on riskier missions that might go wrong sometimes?
Every astronaut gets in a rocket, I don't care how many times that rocket goes up, is risking their life. Okay? No question about it. All you have to do is see what Elon is doing, so after 10, 11 launches of Starship, he's got a long way to go to make that work. The complicated designs, you can test it, but if the engineering is marginal, in other words, you're not completely aware of the fact that it works this time, but there's a high probability it won't work the next time. That's the killer. So as we go more and more commercial, giving commercial companies more of the responsibility to develop these things, faster, cheaper. Shorter schedules, does that make it better? Okay. Sometimes you compromise on some of these things. So there's not just one way, there's many different ways, but there are some basic principles that you gotta cleave to, Once you get a design and you think it's up and running and working, you need to test it as much as you possibly can, and look for potential problems and test those. Test as you fly and fly as you've tested it.
Do you think they should have launched SLS like every 3 months until it
Yes.
worked? Yes?
Yeah, well, SLS is working. It is our super heavy lift launch vehicle.
Yeah, it worked great, but it didn't.
Yeah.
It wasn't flown like 4 times a year. It
Well,
was flown once after 50 years of, not 50, 15 years of development, right?
Yeah. In fact, SLS now three flights.
Right.
Yeah. So we've really done quite a bit of fabulous stuff with the SLS, and it is our only working super heavy lift launch vehicle. There's no other country on the face of this earth that has developed a super heavy lift launch vehicle that can exceed the SLS at the moment. Okay. And so we ought to be using it. There's plenty of things for the SLS to do. The SLS right now can be launched to Mars and drop off a payload of supplies right now. If we define where humans are going to go to Mars, we've got about 40 to 60 tons worth of material that needs to show up there. Okay. If you've watched The Martian, right? They're already on the surface. They're walking around. Well, what's there? The Mars Ascent Vehicle. What's there? The habitats, and the habitats are running. They're growing. They brought food with them because it's a short stay. If it's a long stay, they're going to have to grow food, and that's what he does. He figures out how to grow food. Well, we're going to drop off an infrastructure that grows food. I mean, all that stuff's got to show up before the astronauts do, and the reason why is when the long journey for the astronauts, we already know that when they land there, they're hardly going to be able to get their bodies accustomed to 40% gravity. Okay, they're going to crawl out of the capsule, and a car, a Waymo car, is going to show up. They're going to get in it, okay, and it's going to take them over to the habs. And the habitats are nowhere near the landing area. Can't do that. You might crash it, right? They're going to be way over there. So all that infrastructure, we can do that now. The SLS can drop off 20 metric ton to Mars right now, okay? Wow. It needs to test capture. Okay, we've done aero braking with satellites, but not aero capture. We need to fly right into the atmosphere of Mars and come out with all that momentum, or most of that momentum, taken away, such that we go right into orbit, and then get into orbit, line everything up, and then drop that payload 20 metric ton down on the ground. We can only put 2 metric ton on the ground right now. That's with the small EELV rockets we use. Okay, the EELV rockets, like the Atlas V, okay, that we use for New Horizons and that we use for Curiosity and Perseverance, they're designed to put a lot of payload into low Earth orbit, but to go to Mars, you take away more and more and more and more and more of that mass, and you can only get a couple metric ton to Mars, let alone land it. We need to be landing chunks of 20 metric ton. And the SLS can take it there. That's what it was designed to do. Now, Starship is, another one of those things that's supposed to be doing that. Hey, great. There's absolutely nothing wrong with that coming online. And then we have a competition. We see where we are with the SLS. We see where we are with the Starship. And then the government chooses, and then it goes and does it. But there's no reason right now we can't be going to Mars too. In addition to
you just said there that the SLS can take 20 metric tons to Mars, and that the Delta Heavy, which is like probably half as big as the SLS, it takes like 3 tons or something, you said, or 2.
The Atlas V.
Atlas V, yeah. So is the SLS actually that performative vehicle that it's like?
It was designed to do
like
that.
10 times better.
Yeah, like it's designed to do that. It's designed to.
I had no idea it was 10 times better than the next best rocket for
well,
getting
it's
stuff to Mars.
It's 10% more powerful than the Saturn V.
Wow.
Yeah, the SLS is not a toy. Okay. Now, it's expensive. Yes. It's not reusable at the moment. Okay, they're looking at ways to do that, and there are a couple ways. They're going to have to figure out some of those ways to be competitive with Starship. Okay, but it's not like we launch them, every 3 months. We don't. If we can launch one a year. Okay. Right now, Jared, the administrator, Eisenman wants to build an SLS every 10 months. Great. And then launch one a year. Super. Well, after a few years, you end up with an extra SLS. What are you going to do with that? Send it to Mars. If we do every 6 months, okay, then what can we do? Well, we can then do one mission, one SLS to the moon. Now, why is that important? Because it's taking 35 or 40 metric ton to the surface of the moon, which is the lunar habitat and the lunar base and the lunar rovers and the lunar mining equipment and the ISRU and so you could do, if we were making them every 6 months, you could do one SLS a year for the moon, and then one every Mars opportunity every 23 months. Bingo. Now you got a Moon and Mars program. Okay. What else you have? Well, you actually lower the cost and lower, because your teams are active. They're getting ready. They're building the next one. They're bringing it on. They're keep their skill set high because they have a launch rate. And what happens is they now can figure out ways that they can build them more cheaply. All right. And then go to Mars on top of that, and every opportunity. That is the program you need to go, and you need to get it installed. And he's moving in that direction, and we need to be doing that. And then when other rockets come along, Blue Origin's got their own fabulous heavy lift vehicles. When they come on, more competition is better. But we have a capability now. Let's use it.
Yeah. So I had a question about
Phil,
let somebody
hang
else
on one
speak.
second,
Yeah.
if you would. Yeah. A lot of us had the opportunity to see some of your good public outreach at ISDC, and there was a really nice presentation that you did there with some information about planetary science and our place in the cosmos and ways that we might spot advanced civilizations. I think the Space Show audience would love for you to share some of that outreach with us. Would you be willing to do that?
Yeah, of course. My pleasure. This is research I've been doing in a related but slightly different field. Okay. Really big into space weather. That's actually how I broke into this field. And now I want to look at what happens outside our heliosphere. What happens beyond that. And then what happens as we move around the galaxy, and what does that mean for other civilizations? How do they orbit the galaxy? Are there dangers out there? Are there ways that we can leverage some of these new findings to understand what's happening? So with that, let me go ahead and talk a little bit about that. And this is some research I've been doing with others. Let's see. All right. Can you see this fabulous set of molecular and other type of clouds and the heliosphere? Well, the heliosphere, from the Voyagers is about 120 AU. It actually has a complicated structure when we really do our modeling and look at it. And humans have really come up into this exciting age of the modern Homo sapiens in the last, 30 or 40,000 years. And all during this time period, we were in what's called the local interstellar cloud. This cloud has really protected us very nicely. And what do I mean by that? Well, 70% of the cosmic rays don't get in. All right. Our heliosphere is preventing them from getting in. But we're moving out of the interstellar cloud and we're moving into a new cloud called the G cloud. In fact, current research seems to indicate we're already in this interaction region. Within 1,000 or so years, we'll be well situated in the G cloud. Now, a lot of people will say, okay, well, 1,000 years, I'll be dead. Okay. But in reality, we need to be thinking about how the human civilizations that we have survive. We cannot survive without knowing what's out there in space. We cannot ignore what will happen to the Earth as the sun evolves, but also as we go around the galaxy. All right. So what our heliosphere actually looks like, when we do the MHD modeling, is this. We have the local interstellar medium hitting our magnetic field structure of the sun, and it sweeps it back, and it looks like a croissant, okay, as it moves forward. And we know very well what's inside the croissant, because that's all of our main planets and our sun, along with all the space weather, is there. But what's outside that, and should we be worried about it? And yeah, as I just previously showed, we're moving from cloud to cloud to cloud, and some of these clouds are really dense, and it's going to squish our heliosphere. So our heliosphere will grow and grow big at sometimes and get squished. So how do we go around the galaxy? Well, it turns out we were born in a star cluster above the galactic equator. All right, so we're looking at the galactic equator here. This is where our spiral arms are, and we're actually born above that in a cluster that we think is anywhere from 2,000 to 20,000 stars. And because it was a loose cluster, most of those stars have been moved and pushed out of the way due to a variety of galactic tidal forces, but more than anything else, local gravitational tugs and pulls. Most stars are in the galactic plane, and so we are pulled down to the galactic plane. We overshoot it, and then we come back. And we perform this up and down motion as we go through the galactic plane every 70 million years, and we go from cloud to cloud to cloud to cloud to cloud, all right? So we perform about 6 cycles every 225 million years, which is one orbit around our galaxy. So, well, what's outside of our heliosphere is space weather. So or rather, space weather is inside, but cosmic weather is what's outside. We have winds from other galaxies. Our galaxy is pulling in interstellar matter from several galaxies that are very close to us. We have molecular clouds, we have cosmic rays, we have charged dust, we have bigger dust that's not charged. Some of this stuff gets in. We have galactic cosmic rays, and then we have regions where our solar wind gets accelerated, and we shoot beams of high energy particles back out into the interstellar medium, and that becomes our contribution to cosmic rays. Well, our Voyagers, as you see here, as soon as they passed out of our heliosphere and into this area around around us called the heliosheath. This is that transition area from inside the heliosphere to outside the heliosphere. We then have all these cosmic rays we haven't seen before. Like 70% of the cosmic rays. Well, cosmic rays, are bad for human spaceflight. Cosmic rays change chemistry of our planets. And it's all about the size of our heliosphere. So if our heliosphere goes through various pulses and changes, we could really change the environment in and around the Earth. And so that's one of the areas that people are studying now, and why we want an interstellar probe. So here, on a logarithmic scale, is what we see. We see all the planets, and then we see the heliopause at about 100 AU, and then we see the Oort cloud that's really way out there. But there's another feature that we have found out, and this is an extremely important feature. It's the Lagrange point called L1 of the sun relative to the center of the galaxy. All right? Now, we're all familiar, people in the space business, and now even more so with more of the public, about the importance of Lagrange points. In fact, JWST is at a Lagrange point. So when we launched JWST, we talked about why is it going there? Why is that an important point? We have a ton of satellites at the Earth-Sun Lagrange point. But what is the sun's galactic center Lagrange point? Well, it's right there. It's at about 3.8 light years. So what does that look like? Well, what that looks like, here's the gravity map of what that looks like. You have the gravity of the sun, and it interacts with the gravity of the galactic center, and that includes dark matter. So that's all the matter we see, but all the matter we don't see. This is the latest calculations that have been done, and this is a huge area. It's about nearly 8,000 AU. Well, if here on Earth, when we look and we see the moon, it's about almost 4 times the size of the moon in diameter. So it's a huge area of the sky, relatively speaking. And what's going on there? Well, that's a real minimum gravity area. And we now know that anything that just sort of passes through this minimum gravity area can get captured by the sun. Okay, and if it get captured by the sun, we can bring it in and it can orbit the sun. And that includes anything that might be out there. Well, what could be out there? Well, rogue planets that have been ejected out of other solar systems, don't have a star, can end up moving through this area and coming in. What else could be out there? Well, comets could come in. We now see that there's been several interstellar comets that pass through our solar system. They always have. We're just now getting good enough to see them. But neither one of those have passed through this area. They've all passed through other areas. So that means they aren't going to be captured. Yes, Marshall. You're
muted. Turn your microphone on, Marshall.
Yeah. I've done quite a bit of reading on the local super bubble and the fact that basically our solar system is kind of in the middle of it. And what's going to be the effects when we move out of this super bubble into the thick galactic winds and materials and more suns?
Yeah, we're going to move into another cloud. It's called the G cloud. In fact, we're making that transition right now. Our heliosphere will shrink, and it may shrink to within 5 to 10 AU. Now that's really phenomenal. And in fact, we believe several million years ago that we passed through even denser clouds where the heliosphere shrank to less than 1 AU, and that pops the Earth out into interstellar space. So our environment isn't of the sun anymore with space weather, it's of cosmic weather. We actually believe it happened during the time that may have produced what's called snowball Earth, where the Earth got really cold, and a lot of Earth scientists like to look at that and think about, what are the reasons that Earth did this to itself, ignoring the fact that it actually may have changed the environment that it sits in. With the heliosphere coming in, then the cosmic rays hammer you. It also brings in charged dust particles because you don't end up pushing them aside at the heliopause because you're outside of that. That scatters sunlight. So to go through a snowball Earth, it might be as simple as creating more clouds because the cosmic ray precipitation and a lot of dust that then scatters sunlight. We have less sunlight, and now we have a planet that can freeze. So these are the kind of things that we're just now becoming aware of.
And what about interstellar objects?
Yeah, well, those interstellar objects still are managed by the gravity of the sun, okay? And so they're still going to be they're still going to be trapped or not trapped by the sun by going through this porthole, going through the sun's L1. Yeah, Philip.
Yeah, so I heard that there was some sort of asymmetry in the Oort cloud objects that suggested to some that there might be a planet X out there. I was wondering if maybe this minimum gravity region and the way that objects would get captured by the sun could be an alternate explanation for that asymmetry.
Yeah, it can. I agree. So, what I talked about at the ISDC was really all about how this could be used by advanced civilizations. Okay, it's a crazy idea. Okay, but if you're thinking ahead of intelligent life in our galaxy, and they want to look at us and they want to determine, is this a solar system we're interested in? Is there life here? How would they do that? Well, they actually could go to this minimum gravity region and stay there because the gravity lines that you see are the roads. When we think of interstellar travel, we're not thinking about what the roads are. We sort of think, well, we're going to make our own road, but our roads are really made up of understanding the gravity fields and how they interact. You're looking at a road map, and I mean that figuratively. So aliens could come to this region, could if they're going to master interstellar travel, they're going to be following these gravity maps, and they're going to go to this point. They can go and sit there for a long period of time and not have any fuel expended. This is one of the nice things about it. They can sit there and orbit that point, just like we do with all our other satellites, and save all the fuel. Well, we all think that fuel is important. We all work hard to conserve fuel because we only have so much of it. You have to follow these gravity maps, and then you go to a place where there's minimum gravity, like this Lagrangian point, and orbit it, and you can and the sun and the galactic center drags you along. You don't have to worry about it. Okay, so what could be there? Who knows? We haven't really looked, right? So advanced civilizations, if they wanted to take a good look at what's going on in the solar system, and sit there and look at planets, see what's happening, this is the place I would go to. All right, and we ought to be looking at what's in this area. Okay, we ought to be looking at understanding how things can get in and be captured by the sun that could be hazardous to the Earth. And of course, how we might use it as we become more and more advanced in our own civilization to be doing interstellar travel. This indeed might be the way to go. Okay, so it's a crazy idea, but it's all about some of the latest research that's being done in this area. So what do we know? Well, we know our heliosphere is surrounded by cosmic weather, and that cosmic weather changes depending on the clouds that we go through. And we go through a lot of clouds because we're not in the plane of the galaxy. We're not all moving around together. We're going up and down, and we're going from cloud to cloud to cloud to cloud to cloud. Some of these clouds are dense. The G cloud is 30 times denser than the cloud we're in right now. And we're going to be well situated in the G cloud in about 2,000 years. And we got to know what the gravity maps are in and around the sun to understand what can come in and what through these kind of stable orbits.
So what's changing there? The dark matter? Is that's what changing, because the galactic center is not changing, right? So
correct. So we don't think the dark matter is changing either. Okay, But this location at 3.81 light years between us and the galactic center is calculated using the latest models in dark matter. Okay. If we dropped out the dark matter, it would shoot way up into towards the galactic center by 12 or more light years away. It's dark matter is really what's bringing it close to us. And so, indeed, any advanced civilization running around the galaxy is going to have to use these the gravity maps to understand how to go, where to go, and what to do. I mean, if you think about the Federation, from a science fiction point of view, this obviously is Deep Space Nine, and if you think about where would you go to meet with many different civilizations coming together, you would meet here. You would meet at a Lagrange point. This is where a station can survive for long periods of time with moving around the galactic center, be centrally located to a series of other stars with other civilizations. They all have their own L1s, their own Lagrange points, and be able to move between them. All right. Yes, John.
Yeah, I was reading your papers there before the meeting, but I was thinking about this. What about the other stars that are here, local stars, the Alpha Centauri and so forth? Wouldn't that also create a gravitational thing?
It does.
With the sun.
It does. It does.
And
there'll be another Lagrange point with respect to those two. That's right.
But
Now,
does this totally dwarf that in terms of effectiveness? What you're showing on the galactic level?
No, not necessarily. It just brings up the concept that we're so used to Lagrange points between the Earth and the sun, or the moon's L1. The sun has them too.
Yeah.
So we haven't done the calculations between the sun and Proxima Centauri, which is our closest star. But that would also form another minimum gravity area, which would let in matter. And if we wanted to go there, because it's got planets, planets the size of the Earth. They're not Earth-like; they're very different, but they are about the size. One of them is you would use your gravity fields and go to a location like this and stick around for a while and observe it.
Okay, that's interesting.
Now, what else is there? Okay, as you go from one cloud to another cloud, what accumulates in this region, particularly if the velocity is not very moving very fast relative to the sun, is dust, interstellar dust. So you can imagine this region starting to fill up with interstellar dust. Well, that's fantastic. You could actually run around scooping up that dust, all right? And then you use it as a resource. So imagine the ability to bring that material in. Well, what's in interstellar dust? All kinds of stuff. Silicon, graphite. You've got all kinds of materials, a whole variety of radioactive materials, because dust actually captures radioactive material from supernovas. So you might end up having it as a supply of material that is used for fuel or used for other resource purposes. So any place where you can go where dust gets accumulated, like in this particular area, is a resource. You can do the in situ resource utilization, the ISRU as we call it, of our solar L1 is dust, is the interstellar dust. Now, some of the interstellar dust will go through our heliosphere because it's large, and even though it may be charged, but most of the dust is charged, and so it doesn't make it into the heliosphere. And so this is a great little area to explore. And we can do it with telescopes, but we haven't done any of this yet.
Okay, yeah, I was just going to.
Is that
Sorry,
dust? I'm sorry. Is that dust mostly made up of hydrogen, or
No,
it can also
No.
have other
Yeah, so-
elements
yeah,
already established?
all kinds of stuff is in interstellar dust. Interstellar dust is made during certain life cycles of certain stars. Okay, think of a red giant, which expands its outer surface, and the surface is much cooler than it is when the sun is a smaller object, you know. And so what happens out there? Well, now material can coalesce. Now you can start getting anything that's in the atmosphere of a red giant is at a much lower temperature, and you can actually create dust. And then the winds from that star push that dust outward. So these are real dust generating systems. So the more these stars go through their life cycle, the more they create dust and push it out into the interstellar medium. And then it drifts through our through the galaxy, and therefore through our heliosphere.
So they can be made up of elements beyond periodic number 20.
Oh, yeah. Oh, and typically they are. They'll have actually iron 60 and beryllium 10, and they'll have, you know, every up and down the chemical chart, the periodic table, all over the place,
including actinides.
Okay, so that's some of the stuff, some of the crazy stuff that we've been doing.
Jim, can I throw another crazy thing at you?
Well, of course.
So I've been searching for a satisfactory answer to this one for the 25 years I've been doing the show. But so I'm not an engineer and I'm not a scientist. My formal education is business and liberal arts and history and all of that good stuff. And so, and I know the people here are engineers, and they get into minutia and the weeds about this little thing, that little thing. But it seems to me, if I'm looking at this, and a lot of it I don't understand, and some of it I do, and I don't think a lot of the people understand. So in many ways, we all can't participate in this puzzle, but it seems to me like somehow we have this incredible puzzle, and the only way you can solve the puzzle is to research and learn more about all sorts of little things in the puzzles, because as you learn more, you get to a different layer of the puzzle. So I come to the conclusion that we're being played with somehow, because there's no solution to the puzzle ever, because nobody's going to live long enough to get through all the layers of all of the puzzle for the entire universe. But the more you learn, the more you don't know.
Yes.
This is
the more you realize you don't know what you don't know.
If someone had done this as a computer game, either this would be the most successful barn-burning game to play, or everybody get frustrated and throw it in the river or the toilet or something. How do you see it as a big picture? Because somehow we got an organized structure puzzle, and figure it out if you can. And so, some of us can figure out more of it. Then some of us figure things out through literature and poetry and art. But that's what we're talking about tonight. But here's the puzzle, guys. See if you can work it. And of course, you can't work it because you can't ever get all the pieces of the puzzle put into the puzzle.
So I appreciate what you
what I mean?
Yes, I appreciate what you're saying, and what you're really talking about is the scientific process. All right. What is science? Science is the study of the nature of things. All right. And as you study those, you use it from a framework, and that framework are what we write down mathematically as we understand it, what those things have to obey, and we call those laws. So we have Newton's laws, and we have Kepler's laws, and we have Einstein's equations, and so we want to express our knowledge through mathematics, but in reality, we may not have all the mathematics we need. We may not have an understanding of all the laws. To me, I think in cosmology, for instance, in my lifetime, we've gone from, what we see, we have to figure out what's happening using theories like the Big Bang. And then now all of a sudden we see things like dark energy and dark matter. And they're called dark because we don't understand them. Okay. And they don't seem to follow the laws we thought we knew. All right. Is there another set of laws? What are we missing? Dark matter, for instance, is also called dark matter because we think it's mass, but you can't see it. That means it doesn't interact with light. Everything we see interacts with light. Light shines on us and reflects. We absorb light. We emit light. We can bend light. We can bounce light. We can refract light. We can do all kinds of stuff with light, but dark matter doesn't do that. All right? Doesn't interact with light the way normal matter, what we call baryonic matter, does. Completely new concept. I mean, when that started coming out, it just blew my mind. You got to be kidding me, And it just tells me, as you point out, David, we don't know everything, and we're struggling with our ability to learn these things or know the nature of these things with the tools we have. But guess what? We don't have all the tools. You're trying to put in a bolt into a complicated structure, and you only have a hammer. Okay, where's your socket wrench? Well, we haven't invented it yet. Okay, all right, that's the way it's going to go. For some people, that's very frustrating. For others, that's very exciting. The concept, you can discover new things. You can look at things differently, and come to different realizations. For instance, Einstein, almost all the way up to his death, towards the latter part of his life, he changed his opinion. But through most of his life, did not believe in the singularity in his equations that created the knowledge of a black hole. Said they don't exist. Black holes don't exist. He changed his mind, as I understand it, but he had to go through that mental process of figuring out how and why they might exist. And voila, they do. And now we see them. We actually can image them.
Is the puzzle already completed, and our job is to understand and break it down? Or is this a regenerating puzzle? The more you know, the more the puzzle gets developed.
Yes, the more we know. This is all about science. So when we launch a mission, our mission's going to do X, Y, and Z. Going to make these measurements. So it goes to where it needs to go, and it makes those measurements, and then it finds out, well, look at all this other stuff. Where did that come from? And so new discoveries are made, and those new discoveries lead to new questions that need to be answered. And this mission can't do it, so we develop another one. And that's how the space business goes.
So, but is the puzzle already a finite puzzle, or is it a living puzzle that keeps throwing more at us as we learn more? It's like developing on-the-job training for puzzle developers.
Well, what you're saying is is the physical world evolving?
Correct.
Yeah. And there's plenty of indication is yes. Now, if that means it changes the nature of things, that's exciting. That I don't know is happening. Or it means new things can be found that then are discoveries within that framework. So that's very philosophical, David.
That's why I don't get satisfactory answers for the question.
Right. Well, you just have to
That's
deal with
evolving
it.
too, I guess. Marshall, you wanted to ask something?
Yeah. Well, a long time ago, two mathematicians, Lagrange and Euler, came together and did the first second order differential equations to come up with Lagrange points and the Lagrange field. And it's kind of like, oh, wow, we understand this now. And as Einstein came along, his theories came in and we went, oh, we understand it now, which is great and wonderful. And let's see, there was the matrix algebra required for subatomic physics. Wow, we understand it now. We have a long ways to go to understand just what's in our galaxy, and the mathematics and the computers required to do the mathematics are going to be phenomenal by the time we finish.
Yeah, I understand what you're saying. Agree in the sense that the tools that we have are woefully inadequate to be able to describe everything, but they are the best tools that we have based on our ability as a species to create them. So as we learn more, we have to be able to then really scrutinize the laws and change them. So Newton, the real genius in understanding some basic fundamental physical properties of force and mass, his equations are modified by relativistic equations. All right. That is, those processes that you delineate in an equation are different under different conditions. All right. So as you move faster, things get longer. As you move faster, things get more massive. You know, you that comes out of the equations. Light is a particle that can be affected by gravity and therefore can be bent by gravity. You know, light actually, relativistically has different properties. And then you go and prove it. Yes, that must be the case. This is why right after Einstein's equations really kicked off, the very next eclipse, they really did all kinds of work trying to get ready to prove is the mass of the sun able to bend the light around it by pure gravity. And they did that, of course, by looking at the star field before the eclipse. The sun moves in this area. The moon moves in front of the sun. We now can see stars that are behind the sun, and they're in different locations. And that means that light was bent by the gravity of the sun. That proved a number of things that Einstein did, and now you can prove that from a theory into the practice column of the proof. But even that might be modified by a set of other equations that we don't have that involve dark matter.
Yes.
Okay. We don't know.
I wanted to point out, I think that was in Northern Australia in 1927.
Yeah.
And there was a whole group of them trying to get the perfect picture, and they only got one, but it was beautiful.
Yeah.
John, you have a question?
Yeah, well, I just want to mention that these laws that you're talking about, there's what's called a correspondence principle, where the newer law and it can show up the previous one was just approximate version of the previous one, so that Newton, in fact, actually, if you look at the Einstein's developing general relativity, he actually developed the coupling constant between the momentum energy term and the gravity geometry term by simply taking a Newtonian approximation, and then plugging in the values of what that would have to be, and the relativistic stuff got in there, dividing the speed of light and so forth, squared and all that sort of thing. But they approximate, and special relativity, if you let the speed of light go to infinity, turns into Newtonian mechanics, for instance. And quantum mechanics, if you let the Planck's constant go to zero, turns into Newtonian mechanics.
That's
So
right.
they're all interrelated, really.
They're all interrelated. But we didn't know that. What we did is once Einstein's equations came along and we understood the theory, then we jammed them into the classical mechanics theory.
Yeah.
Okay. It's like hidden terms, and everything worked because you were in a particular regime where those terms that were relativistic were so small that you didn't need to worry about them. You can use Kepler's laws to try to go to a planet, but if you don't add a little relativity into those calculations, you don't make it. All right, and we found that out. So,
wasn't that interesting that in Project Hail Mary, Andy Weir had Rocky's civilization not knowing about relativity? I thought that was fascinating.
Yeah, that was cute. That was cute. Yeah, I hope you enjoyed it. If you've read the book, in the acknowledgement, Andy acknowledges myself and a couple others for some of the ideas, and that's in the book. And I was straining my thinking on. I interacted with Andy off and on over The Martian because I was NASA's head consultant on that movie, and I recognized there was an opportunity where Andy and I talked about life like we don't know it. And everything we knew what was going on with that whole field called weird life. Okay, weird life is not carbon based. Weird life is, using different solvents, not water. Now, all kinds of stuff like that. And so he did that, and spoiler alert, is not just one type of life that's not like us. He actually has got two types of life not like us in the movie.
That's right.
So what does that
I've got a
mean?
question.
What does that mean for ET being here and Disclosure Day, since we're into the science fiction part of it?
Right. I mean, you're right. Well, as you saw, I talked about well-grounded observations, what we know, what's happening, some of the latest calculations, and then I added a little science fiction at the end. And that's great because science and science fiction actually does a dance. I have to tell you, I was in high school when Star Trek came out. Now, I loved that. I watched every episode, starting from the very first one. In addition to that, I was working in an observatory when I was in high school, building instruments to the back of a telescope. So, when you think about what was going on in that TV show in 1968, what was happening? Well, Kirk was, using his communicator and talking to Scotty on the Enterprise, and he's on a planet, okay, not Earth. And fast forward in 2015, I'm in Australia teaching a class, and we ended up calling Jessica Meir on the International Space Station with this iPhone, okay? And I was just thinking about it, and it struck me that in my lifetime I saw that. Now, in addition to that, what was Star Trek like? Well, every episode, pretty much, they were going to a planet orbiting another star, okay, looking at different civilizations. When I graduated at the University of Iowa in 1979, and I had an undergraduate degree in astronomy and physics and space physics degrees, there was no hope of seeing a planet orbiting another star. Just forget it. Don't even bother, it's not going to happen. And yet, somebody figured out how to do that, created the instrumentation to do it. And now we know that there's more exoplanets, planets orbiting other suns, than there are stars in our Milky Way. And then JWST is seeing all these planets that are not orbiting stars. They've been ejected out of the solar system. Not maybe ours, but others, through a variety of processes that happen. And these planets are called rogue planets, and they're wandering the Milky Way, orbiting the center of our galaxy, and may actually harbor life also if they have moons, and they're large, and they're tidal forces that melt the water, because there's gobs of water. I mean, our solar system actually is a soggy place. And I think that's true for the rest of the galaxy. So you may have Jupiter-sized planets with moons, like the Jovian Galilean moons, that don't orbit a star and have life. Really crazy stuff going on. All that stuff, I've seen in my lifetime that were just pure science fiction.
AJ?
Yeah. This the point of I guess L1 or whatever, so with respect to the center of the galaxy that you for
solar
sun,
L1
that L1 that you calculated, which is about 3.8 or so light years away from the sun.
3.8 light years,
light years away from the sun. Now, is that when you calculated that, did you include the dark matter in the galaxy?
Yes, we did.
If you did, then the equations that you may have used, that we normally use for L1, are just gravitational equations. And so, would that be proper to use them? I mean, if you don't know for sure if those equations are valid with dark matter, so can we definitively say that could be that, or could be something else?
Well, yes, that's true. That comes from a peer-reviewed paper. All right, and I'll stick it in the chat if you want a copy of it. And it's to the best of our knowledge. All right, it uses our latest mathematical frameworks, includes the top dark matter model for our galaxy, and I hope as we learn more, we're going to find others redoing that calculation and coming up with a different answer. Okay, if that's the case, or we start looking for potential objects that may be in that area. All right, and then if we start seeing them and we start studying them, and we're seeing that they're orbiting in a circle, not orbiting the galaxy, they're not flying by us, but we are dragging them along. Then indeed we have found the real solar L1.
That should be quite interesting to see that. I guess another philosophical point, I suppose, is that Einstein, near the end of his life, not quite the end, but near the end of his life, started believing in God, or if I could be mistaken here, but started believing in religion or God or something of that type. So the question that David pointed out about complexity of all of these things and inability to really fathom or answer for the future, long-term future, etc. Is that why people fall back into religion and God, etc.?
All right.
I mean, is that a fair thing to do?
Yeah. So we are individuals. We are humans. We have coping mechanisms. We have abilities. Not all our abilities are alike. Not all our thoughts are the same. As we navigate life, we have to be able to cope with the environment that we're in. Now, I'm an Episcopalian. I was born in an Episcopalian church. I was an acolyte. I enjoyed the services, and in many ways, I would say I'm not an atheist. All right.
Mm-hmm.
Now, that might look like a contradiction in my life as a scientist, but it's not to me. All right. Because to me, I recognize I don't know everything. This provides me a set of peace. Now, it doesn't mean I believe the Bible word for word. It doesn't mean that I believe in exactly everything that is the current doctrine, but I also recognize that there may be aspects of creation that we don't understand, that we don't really feel comfortable with. So we all have our own coping mechanisms, you know. I would like to think that some aspect of what I know and what I do after I die helps the human race and has an impact. And then I wanna understand what happens next, and the only way we can do that is go through that process. So you have to come to some realization on an individual basis, and that's your faith. But I'm not an atheist.
No, I think that's very interesting that, and of course, obviously the sideline to that is the different religions have different, like Hinduism, for example, which I am, born, that has a lot of mysterious answers for some of these things, which really are interesting to look at, interesting to think about, interesting to think, but still they don't answer all the questions either, and
Right.
neither will they.
You know, I study Kabbalah a lot, which I really like mystery things. Okay, and I like mysteries associated with Bible and God and religion. And I read some of these famous rabbinical Kabbalistic writings. And I just read one on Do Animals Have a Soul? Okay, it doesn't have anything to do with the space show, but I'm reading it, and this very famous mid-century Kabbalistic rabbi is writing how the Bible shows that animals don't really have a soul, but they have this higher level. And I'm thinking, you don't really know that. This is you read what other humans have written about this or that, and then you come up with your opinion, and then you write them, and you have earned the right over ages to be a rabbinical scholar for Kabbalistic views. And so, but the truth is, you don't know any more than I know whether an animal has a soul or not. But I can tell you, I live with my dog, and my dog has a soul. And everybody,
there
you go. And I don't care what the rabbinical church show or a priest may show. There are just some things you kind of know, but the scholars, they're mostly opining on how they understand things. So I think you have to take it all with a grain of salt. But you
have to
know what you know because you had some kind of upbringing. And I think in the end, you have to trust what you know. And I know animals have a soul if anyone or anything has a soul.
Actually, I think my cat is made up of dark matter.
Now, I can't tell you that a crocodile has a soul. Or
we got a couple of questions. We should be taking a couple more questions here.
But anyway, Marshall, you want to say?
No, John was up first.
Oh, John was up. Okay.
Oh, okay.
Oh, I just wanted to kind of something I might clarify what AJ was getting into. The gravitational effects of dark matter, it's the other way around. The gravitational effects is what we infer dark matter from.
Correct.
We'd observe the gravitational effect, and then we
Correct.
postulate dark matter is the source of it, and then
Right.
figure out what characteristics it would have to have the way it is. It's got to interact gravitationally. It doesn't interact electromagnetically.
Correct.
Weak force is a question mark.
Right.
But it
And we
is
don't know
mappable.
we don't know what kind of particle it is.
That's right. We don't
Yeah,
know.
whether it's bigger than a proton, smaller than a proton. The fascinating part about nuclear physics is, decades ago we only had the proton, electron, and neutron, and then when you started recognizing that you can bust the proton and neutron up into smaller pieces, and we started calling them quarks. So those must be the original set of material at the beginning of the Big Bang, and then they go through phases of coalescing and creating this other kind of matter because that vacuum had energy, and Einstein said energy and mass are related. And so you take some of that energy that's in that vacuum and you start creating these masses. And and that ends up being baryonic matter. Therefore, dark matter, if it's actually can be described as a particle, must also have existed at that time, but may not have interacted or created it. It may have been that way, but we don't know. So we'll see. We'll see. They're hotly pursuing it. Somebody wants a Nobel Prize for sure. Marshall.
I think I'm next year, and one of the things that fills in what David was saying and AJ was saying and you were saying is how do each and every person handle what we don't know? And as a mathematician, physicist degree, I learned very early I didn't know squat. And you have to be comfortable with not knowing.
Correct.
It's fun. It's fun to read about WIMPs.
Yeah.
And
dark matter WIMPs.
Yeah. And then you turn around and you go, oh, gee, how did they prove this? How do they? And then you're off just trying to design something, working through some kind of electronic system. That's fun. It's the adventure of life. What we don't know is almost as important as everything we do know.
Yeah. So, but you bring up something, the heart of what we've been talking about from moving our knowledge forward, in my opinion, is that we all come from different perspectives. We all perceive our environment differently. We take certain things and that's knowledge we retain, other things we let go, but the person next to you may retain those things that you don't retain. Our cultures are different, so we have different experiences in those areas. One of the exciting things about science is creating teams with these different perspectives, all right? Yeah. Now, the paper I just put in the chat, which is the one on the solar L1, permanent capture paper, we call it. Ed Belbruno had the mathematics. I had, I brought to that much more of what we can do with that. Why is it important that we calculate the solar L1? What does that mean? Is it something obscure or is it something really tangible, really physical, and is important to know? And how would it be used today versus how it might be used by us as humans 1,000 or 10,000 years from now, if that knowledge proves to be important? So. We each brought different parts of that perspective. And that's what makes these teams, as you come together, really important because you can do all kinds of new and important science. Sherry, you had your hand up.
Right. It's good to see you again. I wanted to ask you something. If my understanding of this is correct, you say that in 3,000 years, we'll be entering a more denser part of the cloud.
Yeah, a different cloud,
And yes, and
the G cloud.
that, yes, the G cloud. And that might be an extinction event sort of a thing, or it might lead to an extinction event sort of thing. Is that correct?
We don't know enough about the G cloud to know how it'll affect our environment. Therefore, we need to study more of the attributes of the G cloud to determine and model what might happen to the Earth.
Right.
We
Okay.
can model what will happen to the heliosphere. The heliosphere will contract. Why? Because the G cloud is 30 times more dense. 30 times. We know if we end up in a cloud that's 100 times more dense, then our heliosphere will shrink to less than 1 AU. So it'll have a long tail, and as we orbit, we'll come in and out of the heliosphere. So we'll experience intergalactic cosmic weather and then space weather, and then intergalactic cosmic weather and then space weather. And those environments will be really different. We'll have much more intense space weather because the heliosphere will confine it and funnel it out into a tail. We'll be passing through the heliopause, and we'll have a stream of charged dust hammering the planet because the heliosphere is plowing through that cloud, plowing through that dust, and the charged dust will accumulate and be more dense in and around these bow shock and heliopause area into the heliosheath, we call it, than it would be when we're safe from those particles because they're charged, because we would be in the heliosphere. So we'll get hammered with that. Now we'll get that a couple times a year. How that affects our weather, we know our weather and climate, rather, our long-term climate, once there's certain forcing functions, if you take those forcing functions away, the climate doesn't change immediately. It sort of begins to relax or coast or increase or decrease in weather or intensity, and that has a certain time scale associated with it. So this is a complicated problem that if we really want to see what happens to the Earth, we need to model it. We need solar physicists. We need heliophysicists. We need astronomers. We need people that do nothing but dust dynamics. We need atmospheric physicists. We need to understand the effect of cosmic rays on our atmosphere. We have all these disciplines that need to come together if they want to pursue this line of research and solve these problems. Okay, that's what's really exciting, because when I got my degree, I was told, we want you to burn a hole in steel. We want you to be an expert in this topic right here, X, because you like it, right? Yeah, I liked it. But I also liked Y and Z, and I like science all over the place. So I was much more of a, yes, I really understood this area. That was my field, a master's degree and PhD in plasma wave interactions. I'm really a magnetospheric physicist, and I worked very hard. I know that field pretty well. And yet I loved all the other stuff. What are magnetospheres like at other planets? What is the magnetosphere of the sun like? What is the magnetic field of the galaxy like? How does that interact with these clouds? All that stuff then just gets me interested in other things. So to really push the envelope of new discoveries requires a team. with really great expertise in different areas that you can bring together and solve some of these problems. Okay?
Seems to me you may have come up with a new term for the Drake equation, because it
Yeah.
may be that civilizations disappear because the heliosphere gets swamped.
Because of cosmic weather. Absolutely. Absolutely. We completely have ignored what's happening with exoplanets. When we see an exoplanet and it's the size of the Earth, and then we want to measure the atmosphere, and we want to hope it's Earth-like and all that stuff. And yet, we don't realize, where did that planet come from in the galaxy and where is it going? Because it is moving in different environments. And does that affect them? We don't know.
I mean, it
It
may well
has
be
to.
that.
To me, it has to.
Yeah, it may well be. So when did Mars lose its atmosphere? I mean, it was a billion years ago, about the same time
Yes.
Earth was snowball Earth, right?
Yes, yes,
That was
yes.
that was 780 million years ago, I think, if I remember right.
yeah.
So
But I also have to tell you, I've started the process of looking at some curiosity data to determine if Mars suffered an environment that was in interstellar medium while the Earth was still in the heliosphere. Our ability to really understand this effect is really at Mars. Because Mars, Mars, and if Mars had it, and it has these signatures, and we know it got hammered, then we got a leg up on understanding its importance. So let me make one other analogy. We know the sun goes through another cycle of really intense storms because of the first one we saw and really understood happened in 1859 by Richard Carrington, where he watched a white light flare occur, and in 17 hours there was this massive aurora, and the aurora went through Canada, through the United States, through Mexico, through Central America, and into South America. If you were in Colombia and you looked up, you would see a red aurora. All right? That's how massive this storm was. And huge currents occurred in the atmosphere, which knocked out 125,000 kilometers of telegraph wire, because it induced a current in the wire. And that was the electrical system. That's the first EMF that we got that really is a wake-up call. That is what Carl Sagan says, these kind of things require, big claims require big evidence. And that was the first evidence of huge changes in our space weather. Now we've gone back and we see it happens all the time. All over the place in history, they see these huge red auroras at low latitude, which can only be superstorms. And some of these superstorms lasted, not like the Carrington event, for 2 days, for 9 days. All right. So there's another cycle of huge, intense things going on in space weather. Well, there's probably another cycle of us moving in and out and experience cosmic weather. And so this cosmic weather, we really need to get a handle on it, understand it better, and then we can model it. And then we can look back at the history of the Earth, the history of Mars, and put it in the context of what's going on. And then we want to also be able to say, okay, here's an exoplanet, may have life on it. Does it have complex life on it? Well, it may have, but it went through these clouds and this effect happened on it, and we can model it. And, it wiped out more complex life through a variety of disasters. That's that's something that we have to consider. We have never considered that in the past. It takes short shrift, from the astronomers and the planetary scientists that just want to look at the body in isolation with the sun. We can model the sun, and the host star. We can model the host star. We can see how it evolves. Therefore, the planet is going to evolve in the same way. No way. No way.
Advanced civilizations have a lot of threats. And
It does. And now we found another
yeah.
one.
Yeah.
Well, that's what that's what's so important about knowing these things. We cannot just ignore space. I would like the human civilization to live for hundreds of millions, maybe a billion years. We could pull off a billion years. That would be fantastic. I would love to see that.
Marcia,
Marcia.
Yeah, let me toss in. I think you were trying to make a reference to the Mayaki events that were even larger than
Even
Carrington.
larger. Yes, that's right.
And they happen. There's so few of them, we don't even know if there's a regular rhythm or anything.
Well, they're scattered.
Yeah.
All right. And you have to be on the right side of the sun at the right time. Okay.
Yeah.
Now we actually have an example of a Carrington Mayaki-like event that happened in our lifetime. And it happened in July of 2012. What happened was several huge coronal mass ejections occurred, but they were on the opposite side of the sun. Okay. And they were seen by the Solar A and Solar B. Those are those spacecraft that were at 1 AU to look at all sides of the sun. And so we really missed a bullet.
Yeah.
We really
what was the X rating?
Oh, that I don't know, but it was quite high.
Well, way above 50.
Yeah, I don't know what it's in the literature.
I'll have to go look.
Yeah, you'll have to go look.
Jim, we're coming up on 2 hours, so that's probably getting late on the East Coast. Does anyone have a final or a concluding comment? Jim, do you want to leave us with great thoughts or?
Oh yeah, I can always sum up. You bet. Maybe there's one or two more questions before I go.
I don't.
All right. If not, well, thanks so much for having me. I retired from NASA in 2022, but you have to retire to something. All right. You have to remain active. And as a scientist, what am I going to do? I'm going to do science. Okay. I think my wife expected me to, after I retired the very next day, come home, turn on the TV, put my feet up on the coffee table, and then fix stuff around the house and mow the yard. I still haven't done that. She's very surprised that, I'm staying active. But to me, science and learning about these things and studying them is so fascinating. I can't give that up. Whether I work for NASA or not, doesn't matter. And of course, my expertise that I've developed in my career is all about space. It's about, the hardware, the measurements that we make, where we've gone, what we've done. And I would just encourage everyone that watches the show to stay curious, learn about things that are fascinating to you, and never stop.
Well, if you keep teaching, we'll never stop. So can anyone join your global class?
Sure.
How do you do it? Could we?
Right.
How do we do that?
So right now I'm teaching during the summer. That's pretty closed. In other words, we've got several things lined up. But if you've got an Oculus and you want to audit some of these things, I'd love to have you just walk into a room and with students and you can see what we do. We've developed in the metaverse a spaceship that orbits the Earth. From there we beam down to the surface of the moon at the Apollo 11 site. We can go into a sample early design of a lunar habitat. We can beam into that and then walk out onto the surface of the moon. We can beam down to Gale Crater. And I mean real Gale Crater, and I mean real Apollo 11. I mean, this is data that's been taken that then has been created into a 360-degree metaverse view, and so you can walk around and see the polygonal patterns and the concretions and everything else that Curiosity sees. And then we have an environment for Perseverance. So, we also have Ragu. We've got asteroids. We also can fly through molecular clouds. And these are the kind of things that this new technology brings. It's very immersive. So if you've got one of those headsets, let me know, and we'll give you a code, and you can come in at a particular time and see what it's like.
Okay. Take you up on it. Thank you very
Good.
much. And I look forward to doing another program with you, because you'll probably know a lot more by the time we do another one. So never ending. Thank you
Yeah.
very much for being with us.
You're
Thanks,
very,
Jim.
very welcome.
Thanks, Jim. It was fascinating.
Okay.
Thank you,
I'm
Jim.
delighted you enjoyed it. Thank you.
Thank you.
Thanks, Jim.
Good night, everybody.
Good night.
Space Show.
Okay.
Well, we covered a lot of ground there.